All right, we're going to talk about today to work on the adaptive pole placement a little bit more. Last time we haven't talked anything about adaptation or PAA. So today I would like to formulate the parameter adaptation algorithm. First thing first, here is a quick overview of what we have covered so far. We have come up with a control structure with some feed-forward components and some feedback components. And the condition that we worked on last time is we worked on the case where the plant doesn't have unstable zeros. So BQ, this polynomial, can be canceled in my control design. And that's what we did. We cancel the cancelable zero in this S, and then this will construct a fixed portion of the placed poles in the closed loop. So the D will contain these stable poles from the zeros, and then something else that we can design, D prime. This is the closed loop polynomial. And then after some algebra, we said if we choose T to be D prime, then we can, in the end, have this very nice scenario where the output will track a desired reference. The key equation that we need to design is this Diophantine equation from last time. And we know it's going to be solvable under the coprime conditions. So our goal, as we said from last time, is to write this with something that's similar to the theta phi product. So let's see how that can be done. We have this Diophantine equation here. So this would give us, let's multiply the left and the right hand side both with y k we'll do k plus d. All right? And this would give us d prime. This is what we want. This is where I want to work on, what I want to work on, my goal here. So d prime q y k plus d will equal to, let's simplify things a little bit, equals to r. And then there's a delay operator that can be that will cancel this plus d here, becoming r d r y k. Then a second component s prime a and y k plus d. Now, this is a function, a linear combination of yk, yk minus 1, etc. Because R is just a linear filter. This one, we can see something that's familiar. AQ inverse yk plus d. This looks so familiar to us because remember our plant model. Our plant model will give us actually AQ inverse And then we can create this plus D sign very easily as well. So what this is really saying is AQ YK equal to Q negative DB and then UK. Or in other words, put this delay operator to the left, it becomes AQ inverse YK plus D equal to BQ UK. So the key point is this looks some mixed multiplications, but this really is just a S prime. Oops. This really is BQ inverse UK. All right? So put this now in, you're going to get is this Y output, D prime times Y, is really a linear combination of the previous output Y and the input filtered by some way. Now things get even better. Look at our design here. S prime times B, it is really just S. So this really just is R, Y, and S, U. Okay, so this looks now quite helpful. We have expressed the output, D prime times the output, to be more specific, as some linear combinations of the input and prior output. And what's even better is, look at these. What are these? R and S. These are the controller polynomials. These come from the controllers. Okay? So if I write it as R, as we have written it down from last time, R is R0, R1, Rn minus 1, and then S from last time, let's write it. Last time we wrote down S prime, so let's say S is S0 and S1 all the way to SD plus M minus 1. UK. So we can write it as, in a vector form, some phi times this unknown parameter of the controller that we want to design. Right? So the controller parameters that we don't know yet, this is what we're going to design, are R0. I'm going to put S first. S0, S1, and SD plus M minus 1, R0 to Rn minus 1. So this would be our theta vector. And the data vector, the regressor vector, is going to be S0 times UK, so this is UK minus 1, UK minus D plus M minus 1, so minus D minus M plus 1. And then the coefficients R0 is operating on YK, and then all the way to YK minus N plus 1. And this would be our regressor vector phi K. So indeed, we can write this term as a product between a regressor vector and the theta vector. So this would be our model of the adaptation process. Okay? It is really nice the way that it has come out. These controller parameters just come directly out of this derivation. And it's quite clean. All right. So this is so in the end, we can write it as d prime yk plus d equal to phi transpose theta. In our system identification, we have expressed y as phi and theta. And then we do y hat as our adaptation to be phi and theta hat. And then we do epsilon. We use the difference to drive the adaptation. So let's now work on this part. Okay, so we have completed the first step. Let's work on this term a little bit more. So when the parameters are adapted, when the controller we're going to have something like this. Focusing on the left-hand side of the picture, when we really update the parameters of R and S, right? So here, we are not updating it. Now, when we update them, it's going to be S hat, and then R hat. YK, and then UK, and this is YD, K plus D, and RK. So this is the desired, this is the coming out of our control design, the closed-loop control design. All right? Before the controller parameters are tuned to the optimal status, this won't be achieved yet. All right? So we need to update it. And when we update it, we need to take a look at this picture here. So this one is good because it contains YD in our picture. So we're going to be able to connect this, bring this into our picture now. We can see, let's just work on the block diagram a little bit. This is saying that UK is 1 over S prime, S hat, and then RK minus this output here. So RK minus this R hat YK signal. So it equals, RK is connected to YD, so we need to bring this step in for sure. It's 1 over D prime, and then YD K plus D. So that's that. Looking at this, without doing any further simplifications, we know that YD is some function of U and Y. We can write the formula slightly differently. to focus on yd to be expressed with some functions of y and u. So let's do that. Yeah. So that's a good observation. So I should write it this way. This is t. This is t. This is t. So the way is to design t to be d prime. There was a typo before. Right? Then it should be d prime. That's even better. It's already having this inside. All right? So very good observation. So yeah, it's just one step away. So d prime, therefore, in yd k plus d, it equals s prime, s hat, uk plus r hat yk. So the d prime times yd, it is actually the same structure as d prime y with everything in the controller parameter to be changing on the fly. So this would be equal to, same thing, follow this logic, you can, everything here about r and s becomes the estimated version. So put hat on them, and this is going to contain a hat, and then theta is going to contain a hat. So it's going to become theta hat and I'm going to put yeah. Okay, so this is the formula for this portion equivalently. Okay, so we have indeed come up with something that's analogous to y hat k plus 1 in our system identification task. So therefore, if the controller is updated very poorly, then this will be different from that. And then the difference between them can drive an adaptation algorithm. So the adaptation will be defined. So PAA finally is going to become, let's define the adaptation error to be d prime y k plus d minus this regressor vector okay? So this reads as follows. At time k plus d, I will construct this arrow using the actual output and the parameter estimate theta at time k plus d. Okay? And the regressor vector is indexed at k instead of k plus d simply because you can see here all the information that we need is up to time k. We don't need anything further than that. So that's why it's indexed at k. This becomes our adaptation error, and then we can write we can change the time index a little bit to write it as epsilon k will become d hat d prime yk minus phi transpose k minus d and theta hat. Okay. This is the a posteriori, and the a priori is going to become d prime q yk minus phi theta hat k minus 1. All right? So the second equation is just shifting the time index from the first equation. And then the third equation is acknowledging the fact that in a priori prediction, you use the information of the parameter estimate for up to time k minus 1. That's the difference between this a posteriori and a priori estimation error. And we can update, we can do, for example, series parallel prediction, PAA, to update theta hat. I'm going to write the write it this way. Theta k is updated by theta hat k plus 1, theta hat k minus 1 plus fk minus 1 phi k minus d, and then epsilon k. This is the a posteriori, and the a priori update law is all right. So the notations are slightly different from system identification because of our time index for phi, but the structure is the same. And we can do update of the adaptation gain. Using the same adaptation law. All right? This is the algorithm, and then let's talk about the stability quickly. The stability proof is similar to system identification now, and we can do similar. We can first focus on the difference between our theta hat and theta. So theta tilde defined as theta hat minus theta. Then from this equation, we can have theta tilde k, just subtract theta from left and right hand side, becomes theta hat k, theta tilde k equal to theta tilde k minus 1, and then f. So for stability proof, we always use the a posteriori version of the adaptation equations. Okay? And then epsilon equals to, from here, we know that from this equation, we know d prime q times y, this is here. D prime q operating on yk is going to become phi transpose k minus d and theta. So it's phi k minus d theta minus phi transpose k minus d theta hat. And it equals negative theta hat, theta minus theta hat is negative theta tilde. So it's exactly the same as in recursive least square system identification. All right? So this gives us the block diagram, equivalent block diagram. Epsilon k and then phi theta tilde. All right, so in equivalent feedback block diagram for stability proof, we have the adaptation arrow coming out of from here and then goes in to drive this nonlinear adaptation equation. Okay, and then generate the theta tilde k multiplied with phi transpose k minus d. So this is the same as recursive least square series parallel adaptation, where you have a unity LTI block and some standard nonlinear block. So it is always asymptotically hyperstable. So we talked about stability. Let's mention a little bit about convergence. All right? This is one difference between system identification and adaptive control. In system identification, we want our parameters to converge to the true values. To reach that, we have some requirements, right? One of the requirements is the U signal must be rich in frequency. All right? So looking at here, let's see what is driving the algorithm. We have some desired reference signal over here, okay? And we don't have, this signal is usually not some random excitation signal. This is some specific signals that we want to track. All right? So there's not much flexibility compared to system identification in the excitation signal for adaptive controls. So therefore, the convergence may not be exactly 100% accurate. So in other words, we may have some ideal controllers that will reach this Diophantine equation, but what we actually achieve, what we can only guarantee is that it's hyperstable, so this epsilon signal will be small. All right? And that doesn't necessarily say theta is converging to theta hat. But on the other hand, if epsilon is small, that means what? That means this one is small. That means desired d prime y minus this adaptive version, they are close to each other. All right? So in other words, we can still achieve this, although we don't have perfect parameter convergence. And that, from time to time, it's acceptable. Okay? So that is the convergence case in here.